session number 14 started. My name is Don Davies of Magnuson Klemensic Associates in Seattle, Washington, and today is the first of today's triple track session entitled Advances in Structural Engineering, Part 1. The next presentation, entitled Elegant Efficiency of Complex Tall Towers, will be given by David Scott of Arup, New York. Please welcome David Scott.
Good morning. I'm going to scale down a little bit now, since it's very difficult to beat that presentation when it comes to height. But I'm going to talk about a different trend in tall buildings that has become more common in the last few years, which is complex and unusual shaped tall buildings. And actually innovative and different tall buildings. And yesterday I had the pleasure to go to Kanchenjunga. I'm very pleased the owner is here today to have a look and see what we're saying. And that is a modest 32-story building. And when you are, but it is a tall building. It is an innovative building. It has a lot going for it in terms of natural ventilation. And it can be relatively efficient and effective, interesting and unusual and appropriate to its position. So what I'm going to do is show you some of the tall buildings that we've been working on that are unusual and how we have made a bit of a difference in what we've been doing to them. So I have to admit that most of my career I've worked on square and regular buildings, and even recently working with SOM again on a 42-story tower in New York City. We were able to make quite a few innovations, and I think that we can't lose sight that we can still make these shorter buildings much more efficient, effective, quicker, easier to build than they have been in the past. And there is still quite a way for the industry to go until these buildings become normal and you don't have to involve engineers because it's almost a given solution. That's not the case. Many buildings of this size can actually be very expensive and inefficient. Here is the tower in Dubai that we worked on, and one of these buildings is, if you just look at the tall building, it's about 550 meters tall. One of the buildings that you see there is $500 million more expensive than the other one. So I'd like you to put your hands up if you think it's the one on the right. Oh, nobody. You all think it's the one on the left. Well, I'll tell you the answer to that later. But about 4 years ago, we got involved in this competition. This is for the Gazprom headquarters in Russia. And it brought home to me that architects are thinking about buildings quite differently than they ever have in the past. And the reason they're doing so is because the computing power enables us to draw these buildings. The computing power enables us to design them, and the industry has developed tools to track and individual building components so we can build much more complex and unusual buildings than we have ever built before. Arup were on 5 out of 6 teams, and we lost. And the winner was on the top left-hand side by Rimjim, and ironically, we are now working on that. But over the last 4 or 5 years in our studio in New York, we've worked on a wide range of really quite unusual and different buildings. And as Bill says, getting them built can be the challenge, and about half of these have gone forward during construction. And this is just a selection of some of the work that we've been doing. But what is of interest to me is that when you're designing buildings, it's learning from different projects and actually applying the knowledge and experience that you gather and developing ideas and solutions. And I'm going to take you through a few of the things that we've, some of these ideas and how we've applied them. But when you're doing unusual buildings that have never been done before, you need to really think about what the impacts are, because there is an enormous amount of tradition in tall building design. And if you're designing without any previous experience, you need to actually come up with appropriate design methods, and you need to think about the design from first principles rather than simply following standard procedures. You need to worry about secondary effects which might become dominant, and you need to look at ways of mitigating your design approach by getting independent peer reviews, or by having sort of, particularly when it comes to wind tunnel testing, Arup have a policy of doing duplicate testing on buildings over 300 meters, simply because we always and often find a large difference between results, and that difference is actually money that the client may or may not be spending or should be spending, and it's important that we understand how best to approach these designs. So this to me is quite an interesting building. It's in Louisville, Kentucky, because what's interesting is the juxtaposition between old and new. It's a residential building. It's low rise. It's not particularly low rise, but essentially the building on the right and left are almost the same from a constructability point of view. The walls on the building, the Libeskind building, which is the curved one, are slightly non-vertical, and we're exposing the roof as part of the architectural expression in this building. It's trying to show that you don't have to do the same every time to actually come up with something that is different, something that is actually cost-effective and easy to build. This is another tower that we're now doing with Libeskind in Milan, Italy. And what we quite often start with when we're working with an unusual shape is we do a quick finite element analysis model to look at where the forces are flowing through the skin, and then we think about different forms of structure. And in this particular shape, we worked with the architect to lean the building. Actually, we lent it a little bit more than it was previously leaning to get the centroid of the weight of the building through the center of the foundation. So as far as the foundation's concerned, it's just a regular building on top of it. And the diagrams in red that you see on the screen are the bending moment diagrams due to the self-weight and due to the wind. And you can see that at the base of the building structure is actually being dominated by the wind effects, and there's very little penalty to the structural design by putting the curve in. And at the middle of the building, where you're getting a maximum bending as a result of this unusual shape, you've actually got a much smaller wind load. So the structural bracing system that we had here was actually very conventional and quite small, and it shows two things. One is that you can do a lot with modest-sized buildings that you wouldn't want to try and do, again, with super tall buildings. This is 32 stories. But it also meant that there is no real penalty in size of structural element to create an unusual shape. But we recognized very early on that the movements during construction could be actually quite complex. It starts off leaning in one direction as you're building it up, and it starts moving the other way. So we needed to start thinking about secondary effects and how these would all work. The next building I want to talk about is under construction in Abu Dhabi. I'm not sure if it's actually going to be completed, although it's now complete up to ground floor. And like many buildings in this recession, has kind of been put on hold. But this is the architectural concept that we started with. And again, we started, well, what do you do when somebody comes up with a shape like that and says, this is what we really want to do? And we start to do a literal interpretation, and then we start investigating different ways of achieving the same intent by investigating alternative structural systems. So this is, here it's a mixture of twisted columns, spiraling floors, cross-bracing, cantilever, large cantilevers, to come up with quite a complex structure. We then looked at a concrete option, which would be rather horrific. And of course, we didn't go ahead with that. And then we started trying to say, well, can we just build it with basically inclined columns that follow the building up? And if you do that, then you get large twisting occurring in the core. And that torsion, as far as the core is concerned, acts just like a wind load on the core. And the core wall thickness with the build that on the left here would be about 4 meters thick. But by leaning the columns in and out of the centroid of the building, which is the middle scheme, we got rid of the torsion completely. And the scheme on the right, we looked at counter-twisting some of the internal columns, again, to balance the torsion. This is the different column layout, so you can see here, and these are the torsional movements that you get as a result of the self-weight of the building, and you can see there's no torsion with the columns in the centre. The architect liked this scheme, and this is what we developed through construction. Again, you need to look at buildability, and like Bill was saying, the columns here are quite lightly reinforced to ensure that they can fit through the floor slab when they hit it at an unusual and different angle. With all these complex geometry, we try and use some form of parametric modeling, because inevitably either the developer, the architect, or the engineers ourselves will want to make changes that have a big impact on total geometry. So this is us playing with different twists. We link this into our structural analysis model. We get some direct impacts on the cores and overall wind loads, combined with looking at different building heights. And so I'll now go give you the answer to the question. This building here is $500 million cheaper than so it's the one on your right is 500 million cheaper than one on the left. And we were brought in quite late to this project. We were the third engineer working on it. And the architect had lots of floor plans, hadn't drawn it parametrically, and they had been through a lot of iterative processes with the client, who said, I really want that building, don't change the geometry. And these are enormous buildings. They're taller than Taipei 101. And the problems were there was enormous overturning. There's large torsions from the internal columns that twisted up. The core was broken and it didn't work. And essentially, we're taking the total load on the perimeter structure. And we ended up moving the top of the tower 32 meters. It still looks as unusual and different. It's quite hard to see it. We fixed the core. We put a series of internal columns to reduce the twist that were vertical, and it saved 500 million, because the scheme we had before, or the scheme that they wanted to build and invested a lot of design work, actually just didn't work. It wasn't a feasible option. And we did say that, and we don't do this very often, if you're going to build that original scheme, then we're not going to be party to it. But the scheme that you ended up with, you can see within that dotted line, is actually just a regular building. And we changed these perimeter columns, and you see there's 8 sets of double columns. With the earlier scheme, they were horrendous. They were 2.5 meter diameter columns, 180 millimeter steel wall thickness, practically impossible. And when we finished with this scheme, they're 1.5 meters diameter and only 25 millimeters thick, because the main structure is the structure within the building that's going vertical. It's not this unusual facade. There's a comparison before and after of the different options. So we've done a number of twisting towers, and our brief on this one was to create a tower that twisted in Songdo in Korea, and one that was effective and efficient. And we started off by looking at the perimeter column options, and you see if these are big buildings. They're slightly taller than Calatrava's turning torso that you can see outside on the Perry scheme, slightly wider, and they twist about the same amount. If we twisted all the columns, then we ended up with a core at the base of about 4.5 meters thick. If we just twisted a little part of the building, then it would be 3 meters thick, and if we just put a little twist along the edge, it would be 2 meters thick. But that didn't suit what the client wanted to do, because in Korea, one of the main objectives is that you can build the apartments that you sell on the ground, take people through it, and therefore you didn't want 100 different apartments. They like repetition there. It's an effective way to sell the units, and they wanted a system that repeated all the way up. And what we started looking at was, well, we've got quite a large core in this building. Why don't we use the columns as a means of vertical support, and then flip the units around so that you end up with intermediate columns, intermediate fin walls at every level. So here is the architectural scheme. You can see how the apartments flip over at each floor level. The fin walls create an apartment which gives you 120 foot of wall with a conventional floor thickness, a perimeter beam which is a 400 millimeter upstand. It's very efficient. It works like a cantilever. You don't need a backspan within the floor plates because the floor sees balance within the system. We did some detailed checking, looking at cracking. We put a little bit of pre-stress in the floor. And we had got, with a conventional solution, we had torsion problems still with something like that. But with the staggered openings in the core wall, we got rid of torsion, which allowed us to get the core wall thickness down to about 800 millimeters, down to 800 millimeters actually. And compared to the three other, we did a total of 8 towers on this site, 5 of which have been built. It uses almost exactly the same amount of concrete, except with our twisting tower, you're actually building the walls between the apartments, so in total there's a 10% saving in material. Recognizing that this was an unusual system for Korea, we did detailed sort of nonlinear analysis just to verify the performance in an earthquake zone, but ended up with a wall thickness at the base of 800 millimeters. And if you compare that with Calatrava's building of the same height, slightly less windy, his building, his is a wall thickness of 3 meters at the base. So it's a very efficient, effective solution. It does what, to me, is interesting about it, is it opens up a whole new language of structural residential towers that are effective and efficient, that can meet some of the new demands to do different things. And very quickly we went through different facades. The facade is very cheap because it's a very regular facade, because the cost is in the excitement of the building is in the architecture, it's not in the facade. So as an effective facade, again, we did some parametric modeling and came up with different options for the facade, looking at the impact of different twists, because the amount of twist actually doesn't have a structural implication, and ended up with a very efficient, effective building, which gives opportunities for similar buildings around the world. Thanks very much.